start with control system. So we have been doing problems. You have completed the previous problem. Have you completed the previous problem?
Yes, sir.
Okay. So we will do with the next one. So all of you got C of t is equal to 0.1167 plus t plus 0.12 e to the power of minus 10 minus e to the 0.03 e to the power of minus 60t. So once you complete it, you can note down this problem. The unit step response of a control system is in figure. Find the transfer function for the prototype system using the model of second order. So here what you can see here is here you are given with the figure where you can see that the values are given in the figure itself. So you can see here the value is given as 1.163 and 0.363. So we have to use these values and solve it. So you can just note down this question. The unit step response of a control system is in figure. Find the transfer function. So you need to find the transfer function for the second order system. So how can we go ahead with that? Any idea? Just complete that problem and then we will proceed further. Draw this figure where the values are given, that is at this maximum peak you are given with 0.363. So you should be able to identify that what this value is, whether it is TS, TP, what the value is. So you have to find out that and then proceed further. So 0.363 is given and 1.163 is given for you. So what is MP is from the maximum till from the maximum till the one value. What is that difference? So that is MP. So we have to understand these things in order to write the transfer function for the system. And one more thing, I have given you some assignment questions on SFG signal flow graph, so you can do that. And one more thing, quizzes I will be conducting today, so that also you can attempt it.
Sir, assignment due date is 12th of June.
Yeah, enough. 5 problems to solve.
Okay, sir.
You do it because it is only 5 problems, no? So still I will be giving on this module one more next week. It's just four problems. How much time it will take? 1 or 2 hours it is enough to solve it. So you can do that. And so what all things we have here? Any idea? Anyone can say what will be here MP? MP.
0.163, sir.
Yeah, 0.163 because you can see that here it is given 1.63. So MP will be 0.163. So you can use the equation and find out what all things are required to write the transfer function of a second order system. What is the transfer function of a second order system? What is the transfer function of a second order system? We have written, no, just so many times this one. Wherever you see, you can see that equation. 1 second. Everywhere we have written that equation. So transfer function means what? So you need to study these things, C of S by R of S. So we have studied, I think, some 5 to 7 classes back. So C of S by R of S is omega n square divided by S square plus 2 zeta omega ns plus omega n square. So you have to find out what all values omega and zeta to write this equation. So it's not that difficult, it is easy. So you can, you got the value of MP, and that is 0.163. So once you got it, how to find out zeta and omega, you have to use the equation for MP. 0.163 is equal to e to the power of minus pi zeta divided by root of 1 minus zeta square. So how to solve it? So you need to take logarithm. So you will be getting, you can write the same equation in this form. So here the important thing is that we know that MP is 0.163. So by using the equation of MP, so if you want, you can write one step. MP is equal to e to the power of minus pi zeta by root of 1 minus zeta square. MP you have substituted here, so then you have taken the logarithm for that. So minus pi zeta by root of 1 minus zeta square is logarithm of 0.163. So you can solve it. From that you should get the value of zeta. You try that. Logarithm of 0.163 you find out, and then just simplify that for the value of zeta. Zeta is the unknown here. So what is the value of zeta you will get? You solve it. See, for the value of zeta, what you are going to get when you simplify it?
2 minutes, sir.
Yeah, do it, no problem. So what is the value you are going to get there? See, you are able to see the document, no?
Yes, sir.
Yeah, find out. So it needs some simplification time. So you need to find out zeta. So these things you need to think that how to proceed with a problem when it is slightly different. Okay, that's why we are saying that solve more number of problems so that it will be helpful for you. You will not be seeing a unknown problem. So different types of problems is what
Sir,
we are.
zeta is
Yeah, tell me.
0.474.
Yeah, it comes 0.5 close to.
Yes, sir.
So zeta is 0.5 you can write. So then what else is required for you? So from figure we can have this one. So here you got when you solve it 0.5. Everyone got it? Others also you got that zeta value?
Yes, sir.
Okay. So from figure what we can write the peak time, that is TP. TP is 0.363 seconds. So here it is there. So this is the peak value TP and it is given. So you can use this equation and then find out zeta is already known to you. So TP is also known. How to do with it? How you'll further proceed? Just think and tell me how you're going to do it.
TP formula is there, no, sir. To find out TP, we can use
Yeah.
that.
And what you are going to find out?
Omega n.
Okay, go, proceed then. Okay, so TP is equal to pi divided by omega n root of 1 minus zeta square. So here by using this equation, you have the value of this one TP. So substitute that 0.363 pi divided by omega n root of 1 minus zeta square. So zeta is 0.5. Substitute that, you find out omega n. So let me see that what value of omega n you get it. So you need to study the concepts properly. It will become easy for you to understand if it is, see, this is not a straightforward question that where you can directly use the equation and do it. You have to think that when a figure is given, values are given, what are the values given, how to solve it, how to substitute and get the transfer function. So what is transfer function equation? What are the unknowns in that transfer function for a second order
So
system? So these are the analysis you should have. Yeah, tell me.
omega n is 9.98.
Yeah, anyone else also got it? Omega n? Any other answer? Omega n. What about others? So just respond to that. What about others? Anyone of you got omega n? Or you are still doing it? What is the value of omega n?
9.98, sir.
9.98. Anyone else got any other answer or it's the same?
10, sir.
Yeah, fine. 10. Okay, next, every one of you got it? Okay, so you got that answer for omega n. So by solving it, you will find that only unknown is omega n, and when you simplify it, you'll get 9.98, or you can just write it as 10 radians per second. So if you have used all the decimal places, I think it will come very close to 10. So omega n is equal to 10 radians per second. So now how to solve it further? So what is transfer function? So I have told you just in the beginning also, C of S by R of S is omega n square divided by S square plus 2 zeta omega n S plus omega n square. So from this, you got all the values of omega n and zeta, substitute those values and write the equation for transfer function for a second order system. So it will be 100 divided by S square plus 10s plus 100. So this is the answer you are going to get for the transfer function for a second order system. So all of you completed?
Yes, sir.
Okay. So let us proceed further with the next topic, that is called as steady state error and error constant. So write down this heading. We usually ask this question, steady state error and error constant. So write down this steady state error and error constant. So we will just go with a few equations in order to find out the steady state error and error constants. So the steady state error arises from the non-linear sources. So this is what non-linear sources such as backslash and gears. So in the practical scenario, in the when you are functioning with any device, this steady state errors and error constants. So what we are going to see when you are in a industry, or you are in a when you are having a mechanism to adjust the working principle of a flight and all those things. So you have to see that is there any errors getting generated, or everything is going fine. So once any error just pops up, so you have to rectify those things, and you need to find out the occurrence of error by using some of the equations of how to find out the error constants and steady state error which gets generated in the system. So it's very important for us to know that how best you can reduce the C. So, some things like noise, errors, and all those things, we can reduce it. We will not be able to eliminate it completely. So it may be 0.01 or maybe 0.001 accuracy and all. So it depends on how best you can reduce the errors in order to make the system function properly. So this happens in gears, or in motor that functions in the regular intervals of time, and when it moves further and further, so it may also it's very important for us to calculate. And you know that when you design a system, you design by using different kinds of tools, and you see that the working of each system, whether it is fine. So it is uh, very much complicated to analyze each and every part of the system. So if you see that aircraft only, you can see that the cabin is having a lot many combination of systems which function together to achieve the process of whatever the system entire system has to achieve. So that is so each is a minute change in that can lead to a huge disturbance, and which can finally uh, make the system unstable. So it's very important for us to calculate each and every parameters, and when you are doing the design process, you need to understand that how best you can evaluate those constants, and you can eliminate as much as possible in the design process itself. So when you are just slightly optimizing the sum of the parameters, you can see that this can be like you can see that when you take the transfer function, it is basically depending on zeta and omega. Similarly, when you calculate the errors at different uh, error constants, you can see that it depends on certain variables, and by adjusting those variables or optimizing those variables to the maximum extent in the design process itself, can reduce the errors to the max to the minimum. And you cannot say that it may be sometimes accuracy will be very close to what you are able to achieve, means what your target is. But you can say that sometimes some functions, like some of the things like spacecrafts and all those things, need very precise accuracy, and where you need to have within 0.001 or 0.0001 errors is only tolerable for that. Uh, so some systems will be there at the industry level which can which will be okay with zero point 0.1 or 0.01 error constant. So it's very important that how best you can minimize it and have a smooth functioning of the system. So you can just write down. We'll be coming out with a few equations to calculate these things, and we will try to solve some problems to how to find out the errors, and uh, it can be calculated when you are working out with any of the systems. So write down the heading: steady state error and error constant. So this you can write. So this is the same figure what you have been drawing, that is the negative feedback. So it is it's a considered a system, and the error will be you can see that the feedback mechanism. What is the main role of the feedback mechanism? It is going to take the input and push it to the output, and need to compare it and rectify if there is any change. It is like a continuous process, so it keeps on doing it. And when the errors are generated, so in the subsequent process, it keeps on reducing. So that is what it is going to happen. And so you can see that we'll be studying how to calculate this value of ES and all those things. So you can just note down. We have completed this, we will move further. So write down this. It's an important topic: steady state error and error constants. So draw this figure. It's a negative feedback system. So all of you have completed.
Yes, sir.
Okay. So draw that figure as well. So all of you have completed this. We'll move on next. So have you completed?
Yes, sir.
Okay. So we will continue further. So as I have told you, we will be having the steady state error, and we'll be calculating those things. So we will try to uh, find out the specific equations in order to calculate that. So the steady state error for a unity feedback system can be calculated by using the equation ESS is equal to limit t tends to infinity R of t minus C of t. So you have to take the limit of t tends to infinity. R of t minus C of t will give you the steady state error of a unity feedback system. So when you the error in Laplace domain, you can write it as so this equation is important. So this can be from the same, we can write it as ES is equal to RS minus LS, CS. So, so this is also written as CS is equal to. So we know that if you see uh, So you write down error in Laplace domain is E of s is equal to R of s minus C of s. So you can just this is what error in Laplace domain. So you just go back to the figure. You can see that E of s multiplied by G of s. If you take E of s multiplied by G of s, you will get C of s. So I can just write it as C of s is equal to E of s multiplied by G of s. So I get C of s is equal to E of s multiplied by G of s. From there, I can just we also know that C of s for transfer function of a first order system, that is C of s by R of s is equal to G of s divided by 1 plus G of s H of s. These are the equations which you have studied before, except this equation for error in Laplace domain, E of s is equal to. So these two equations it is known to you, this equation as well as this equation. It's already discussed before that E of s is C of s is E of s into G of s, and this is the transfer function that is C of s by R of s is equal to G of s divided by 1 plus G of s H of s. So here you got a few equations like E of s is equal to R of s minus E of s, C of s is equal to G of s into E of s, and C of s by R of s is equal to negative feedback system. So it is G of s divided by 1 plus G of s H of s. And if you see the figure, since it is a second first order system, so we also know that H of s is 1 there. If you see the figure, H of s is 1 here, H of s is 1, and so we are going to substitute and further simplify it. So when you put H of s is equal to 1, you get C of s by R of s is equal to G of s divided by 1 plus G of s. So all of you got till here? Substitute for H of s. So here we have used a few equations like equations for E of s, that is R of s minus C of s, and equation for C of s. From the figure I have told you, it can be written as E of s into G of s, and transfer function for a first order system you have already studied. It is G of s by 1 plus G of s H of s. Since the feedback is 1 or H of s is equal to 1, you can rewrite the equation as C of s by R of s is equal to G of s divided by 1 plus G of s. So this much you have you completed till here?
Yes, sir.
Okay. So we will continue further. So here what you can see, now I have an option to substitute the terms. So in this, what you can see that C of s can be written as G of s into R of s. So I am just multiplied that C of s R of s with G of s. So I can write C of s is equal to G of s into R of s divided by 1 plus G of s. It's given as equation number 2. So now you can see that let me just take equation 1 and equation 2. You can see that here equation is C of s is E of s into G of s. Here the equation is C of s is G of s into R of s divided by 1 plus G of s. So let me just equate both C of s together. So you know to equate equation 1 and 2. So by equating equation 1 and 2, I can just write it as E of s G of s is equal to G of s R of s divided by 1 plus G of s. So all of you do it here, and if you have any, is it clear for everyone? So you complete it. Till here what you have done is just equating the equation 1 and equation 2 So because both are in C of S, so you can say that E of S, G of S is equal to G of S, R of S divided by 1 plus G of S. All of you got it till there?
Yes, sir.
Okay, you complete, all of you can complete till there. So now you can see some of the terms are quite common and can be eliminated. So we can rewrite that equation further as E of S is equal to R of S divided by 1 plus G of S. So all of you got the equation till this. E of S, what we have told the error, E of S can be written as R of S divided by 1 plus G of S. So this we are studying for first order system. So you can see that we have written the transfer function and all for first order system, that is G of S divided by 1 plus G of S H of S. So all of you got the equation for E of S as R of S divided by 1 plus G of S.
Yes, sir.
Okay, then everything is clear till here. Is that clear till here? Any doubts? Is it clear? See, it's clear
Yes,
for all
sir.
of you. Okay. Steady state error, we have to do that. So steady state error is given as ESS. ESS is called as the steady state error, and which can be written by using the equation limit of t tends to infinity E of t. So by using the final value theorem, what you can write ESS equal to limit of t tends to infinity E of t, and where you can just write it as limit of s tends to 0 s of E of s. So we are going to substitute what E of s we got in this equation. So I need to substitute this E of s here and simplify it further. So you can see that I have substituted for E of S. So I get limit of S tends to 0, S into R of S divided by 1 plus G of S. So my equation for ESS will be, that is called as the steady state error, ESS. SS stands for steady state. ESS is steady state error, and that can be written in terms of RS and GSS. Or you can write in terms of ES as well, that if you write in terms of ES, it is limit of S tends to 0, S into E of S, or you want to write it in G of S and R of S, you can write it as limit S tends to 0, S into R of S divided by 1 plus G of S. Now we will have some of the uh, steps that what we have to understand. We are going to use now different test signals, like what are the test signals we have studied? Any one of you in the starting of the class, when we started this module 3, we have studied unit step response, ramp response, as well as parabolic response. So we will be seeing at different uh, responses how it will look like. So we'll start with one by one. So what we got here is final value. By using the final value theorem, steady state error is this equation. So once we complete that, just you can write, we are going to use the unit step function, first one. So for unit step function, R of t is equal to U of t. So first, so we'll be seeing three cases. So case 1, case 2, case 3, or you can call it as corollary 1, 2, 3. So R of t is equal to U of t, and this is for unit step function, and we are going to simplify it further. So when you take Laplace transform for R of t, you know that it is R of s and it is equal to 1 by s. These are all not new for you. We have been doing from the beginning of the this module. So what you can see here, R of see, you should underline this unit step function and this one, because we are going to do it for the unit step function. So that's the reason R of s is equal to 1 by s. So let us see that the steady state error for a unit step input is, so we can just write it as ESS is equal to, what is the equation? Limit of s tends to 0, s into R of s divided by 1 plus g of s. I am just writing the same what we wrote before, same equation once again. This is the same equation of ESS. We got R of s is equal to 1 by s since it is a unit step function. So let me substitute R of s there. All of you substitute R of s. So you will be getting limit of s tends to 0, s into 1 by s divided by 1 plus g of s. S gets cancelled. So what you will finally get is limit of 1 divided by 1 plus g of s. So g of s, since s tends to 0, we will say that limit of s tends to 0, 1 by 1 plus limit of s tends to 0, g of s. So this term, that is limit of s tends to 0, g of s, is denoted by the letter kp. This term is denoted as kp. So what is kp? Kp is limit of s tends to 0, g of s. So this term, it's just a notation. It's just a notation called as kp, and kp denotes limit of s tends to 0, g of s. And it is defined as the potential. So this is the name given for that, potential static error constant. So what equation we are going to, this equation is very important. We are going to use these equations further. You can see that the equation for ESS can be written as 1 by 1 plus limit g of s, or this equation is very important. That is, it can also be written as 1 divided by 1 plus kp. So all of you can put it in square brackets, in just a box, and just write ESS is 1 by 1 plus kp for unit step function. Okay, so where kp is limit of s tends to 0, e of s, and this is defined as the potential static error constant. So still we'll be further going little more in depth. We have studied all these things. So steady state error for type 1012 system we'll be seeing. So those things we will carry out in the next class. Is that clear for all of you? And all of you have got this equation for this one? That is for unit step function, ESS is equal to 1 divided by 1 plus kp. Any confusions or any doubts? It's clear for all of you? Is that clear for everyone?
Yes, sir.
Yeah, it is just simple substitutions. We have not done anything great too much here. So it is just what you have to remember here is, for a unit step function, ESS is 1 divided by 1 by 1 plus kp, and equation for kp is limit of s tends to 0, g of s, which is known as the positional static error constant. So positional static error constant kp, and so all these values we got, we have to do it for type 0, type 1 and type 2 system. So we'll be doing it, continuing this further for the steady state error and error constants. Still a lot many things are there for you to understand. So we'll stop it here for today. You have your assignments, you can complete it. Even quizzes also you can complete it off, and we will get back to you with this error constants in the next class. Okay, so we'll wind up for today. Thank you. So that's all from my side. Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Thank you.